Bismillah ar-Rahman ar-Rahim. Welcome to Tahar Scholar. I first apologize for this delay because I had some problems in my previous condominium. I am now in a better condo. So let us focus. In this series of practicals, I will introduce Matlab, both as a software and as a language, how to program with Matlab. There will be probably 4 to 5 practicals. First of all, the software we will use is GNU Octave, not the official Matlab from MathWorks. So GNU Octave is completely free, and it is compatible with Matlab. Almost everything you can write and with Octave, you can execute on Matlab, on the official Matlab software. The software actually is an IDE, an integrated development environment, an interpreter, and also a collection of functions, a library of functions that will help you to write your code easier. So this is the official site of the GNU Octave, Octave.org. You just have to go to the download page, and this is the download page. You look for your system. I am currently using Microsoft Windows. I downloaded the executable for 64 bits and installed it. The installation is very easy, very simple. You just follow the instructions. If you are on Linux, you use the package manager to install Octave. For example, I used to use for many years Manjaro, and they have a package manager called Pacman, and it's very easy, very simple to install. And actually, it works a little bit better on Linux than on Windows. I mean, the interface, the graphical interface, the GUI or the GUI, works a little bit better than on Windows. So let us go to the IDE, to the integrated development environment. Take a look at it, and then we start our practicals. So this is the IDE. This is the graphical user interface of Octave. And the IDE is composed of the menu. This is the menu. It has several commands integrated, built in. And this is the toolbar. The toolbar contains actually shortcuts to some commands. And we have 4 windows. This is the main window. And it has 4 window tabs. The current window tab is the command window. Here where we type the commands, and the results are displayed. This is the console of Octave. This is the most important window in the IDE. And here is the file browser. And the third window is the workspace window. Here, when we store variables in memory, the variables will appear in this. All the variables in memory, currently in memory, will appear here with their name and their values. And here is the command history. All what we type in the command window will be stored in the command history, so that we can refer to them later if we want. So let's come back to the main window. As I said, we have 4 window tabs. This is the most important, is the command window. And then we have the documentation. Here you have almost all what you need to know about, particularly about the functions, the built-in functions, the library that comes with Octave. and it's not, of course, a textbook, but all the basics is here. And the third window tab is the variable editor. We can use it to modify directly a variable. I rarely use that. I prefer to modify a variable in the command window or in the editor. So the last window tab is the editor. It is here where we write scripts and functions, and we will use that frequently in the coming practicals. In this practical, of course, and in the coming practicals, we type here the commands and we save them in a file, so they will not be lost when we close Octave. So let's come back to the command window and start our practical. Our first practical, we will focus. In this first practical, we will focus on matrices. So actually Matlab Language, either here with Octave or in the Matlab official Matlab, it has four data types, four major data types. The first is matrices, then strings, then we have structures, and finally cells. So we have matrices, strings, structures, and cells. Matrices are the most important data type. Actually, Matlab means matrix laboratory. So it's the most important data type. And in this first practical, we exclusively focus on matrices. In the second practical, we will see the other three types. And then in the third and the fourth practical, we will see how to implement an algorithm in a function. So we focus on function, how to write functions in Octave or in Matlab. Different, very simple algorithms to understand how to use the language, the grammar of the language, the syntax, etc. So let's start with matrices. So let us first clean the console with the command clc. clc means cl means clear and console, clc. And the first thing to do is to define a matrix, how we build a matrix. So we give it a name, for example, A equals, and we introduce the elements inside the square brackets. So the left bracket, and then we introduce the first row. For example, 1, 2, and 3, 4, and 5. This is the first row. To pass to the second row, we use a semicolon. To separate rows in a matrix, we use a semicolon. And we start the second row. For example, 6, 7, 8, 9, and 10. You introduce, of course, here the values you want. And in this first example, we use only a matrix with two rows. And observe that the number of elements in the first row must be equal to the number of elements in the second row. The number of elements in a row is the number of columns of the matrix. And it must be, of course, consistent, the same in every row. And we type enter. So we have stored in the memory a matrix with two rows and 5 columns. And as you can see here in the workspace, the matrix, the elements of the matrix are double precision. Double precision means 60. It is encoded in 64 bits, and it has 16 significant digits. It can manipulate 16 digits, significant digits. Significance means besides 0, it can store 16 significant digits. And here's the dimension. 2 by 5, 2 rows, 5 columns, and here the value. We can, the values, the contents of the variable. We can double click here, and it leads us to the variable editor, to the window tab of variable editor. And we can here modify directly our matrix. And as I said previously, I rarely do that, but let us try and see how it works. For example, 8, we change it to 8.5. And for example, 5, let's change it to minus 5.7. Type enter. And we come back to the command window and type A again. And as you can see, the variables have changed according to what you have did in the variable editor. So you can change the variable into the variable editor. But I prefer not to change a variable outside the code. Change it in the code, either in the command window, when we write the code, the instructions, the commands in the command window, or in the editor. No, but you have this option if you want. So we have a matrix of 2 rows and 5 columns, and we have introduced it in one single line by separating the rows using semicolon. This is good and useful when you have a small matrix. But there is another way to build a matrix and separate the rows not by semicolon but by new line. And let's do it. First we clear. There's a command called clear. It clears a variable, any variable you want from the memory. Or you type clear all, it will clear all the variables. If you have several, it will clear them from the memory. So here we have only one variable, we clear it. And as you can see here, it disappeared from the workspace. And we reintroduce it again, but this time using a separator, a new line. So we type 1, 2, 3, 4, 5, first row, the same matrix. And here we type enter. Enter will move to the second line. So the first line we type the first row. In the second line, we type the second row. So rows here are introduced by lines, line by line. I move the cursor. It's not mandatory, but for clarity, I type the element one above the other. So here I type 6, 7, 8, 9, and 10. And I close the bracket. And I type enter. And the matrix is displayed. You can also use a command called display to display a matrix. So for example, display, it will display the matrix, but it will display only the contents, not the name of the matrix, and then it's only the contents. If you type A, directly A, or you type your command without semicolon, the variable and its content are displayed. But if you use the command display, it will display only the contents. So this is how we build a matrix. Now what about a vector and a scalar? So in MATLAB actually there is no vectors. The concept of vector, like we study it in mathematics, in algebra, does not exist in MATLAB. MATLAB works only with matrices. So a vector actually is a matrix, can be a matrix of one single row or a matrix of one single column. Of one single row, we call it a row vector. And a matrix of one single column is called a column vector. So we have either a row vector or a column vector. Let's see that in an example. Let's say U is a row vector. And we type here, for example, 0, 1. You can type directly dot 2. Dot 2 means 0, 2. 0, 3. And we close the bracket. And we type enter. So this is a matrix of one single row. It has 3 elements, 3 columns, but one single row. It is a row vector. And for a column vector, we can write like this: V equal, for example, minus 1.5, 2.7, and minus 3.7 e minus 2. And we close the bracket. E minus 2 means times 10 power minus 2. 10 to the power of minus 2. It's not exponential. It means 10 to the power of minus 2. That is minus 0.037. This is the number. You can write it like this, or you can write it like this, 0.037. Same. So we come back to the notation. It's called scientific notation. So we write it minus 37 e minus 2. And if we type enter, this is a row vector. When we need a column vector, so what we do, we add the prime. The prime will transpose the matrix, so a row becomes a column, and vice versa, a column becomes a row. So it's a transpose of this row, and we get a column vector. So this is a column vector. It has one column, 3 elements, 3 rows, but one single column. It is a column vector. We can introduce, we can build a column vector in this way using prime, or we can do it directly. For example, W equal minus 1.5, and we separate the rows by semicolon. But in this time, our row contains one single element. So we type one single element, and then 2.7, the same content as V, semicolon, and minus 3.7 times 10 power minus 2. This is exactly the same as this. Exactly, but this is of course shorter and better. And we close. We don't need here prime, it is already a column. So the first row, one element, the second row, and the third row. And we type enter. And we have exactly the same vector. So again, a vector does not exist. The concept of vector does not exist in Matlab. You have either a row vector or a column vector. So a matrix of one single row or a matrix of one single column. Even scalar actually are stored as a matrix. So for example, let's type A 1.25. Yeah, this is a scalar. Yeah, but in Matlab, it is a matrix of one single row and one single column. And if we type enter, you can see here in the workspace, A, the dimension is 1 by 1. It is a matrix of one row and one column. And you can see here for a row vector, it is one row and 3 columns. It contains 3 elements. And here for V or W, it is one column but with 3 rows, 3 elements. So column vector with 3 elements. And that's it for the first section, how to build a matrix. Let's move to the second section, how to initialize a matrix. How to initialize it, how to set its data, not directly like we have did now, but through functions. So we have cleared all the variables from the memory and cleared the console to start our section on how we initialize a matrix. There are 3 types. The first one is by generating an arithmetic sequence to build a row vector. An arithmetic sequence means the elements, we move from one element to another by incrementing the element with a constant step. And the second type is to generate a matrix with the same constant value. And finally, the third is to generate a matrix whose elements are randomly chosen between a given interval. So the first one, let us take as an example vector u. Let's name it vector u, or row vector. It's an arithmetic sequence that starts with -1, for example, and has a step of 0, 5, and it ends with an element that should not exceed 1. So 1 here is the upper bound. All the elements of the sequence must not exceed 1. There are equals that are equal to 1 or less than 1. So you can see here we use the colon operator. If we omit the step, if for example we write without step, it goes from 1 and not exceed 1, from -1 and not exceeding 1, the step is equal to 1 by default. So let's do that. And we have three elements, -1, plus 1, come 0, plus 1, come 1. But that's not what we wanted. We want a smaller step. So we repeat, and we indicate the step, not the default one, but the given one, 0, 5. And we generate our row vector, an arithmetic sequence. So it started with -1, and then plus 0, 5, and then plus 0, 5, and then plus 0, 5, and so on. So the number of elements in the sequence depends on the step and the upper bound. We can also generate an arithmetic sequence using a function called linspace. So let's name it v, the vector that will carry the arithmetic sequence, and we call the function linspace. Linspace means the linearly spaced elements. The elements are spaced linearly. So what we give as input? We give as input the first element, -1, and the last element. Here it's not an upper bound, it must belong to the sequence. And the number of elements. So let's say 5. We will obtain the same sequence. But here we do not give as input the step. We give as input the number of elements. And the second argument here, 1, is not an upper bound, is a part of the sequence. It must be the end of the sequence. The sequence starts with -1 and must end with 1. So let's type enter. We get here the same. To see the difference between linspace and the sequence with the step, let's rewrite u with the following sequence. It starts also with -1 and end with, not end, as an upper bound 1, but the step here is 0.3, 0.3. And enter. And as you can see here, 1 does not appear in the sequence because we add here 0, 3, 0, 3, 0, 3 until here 0, 3 plus 0, 5. We get 0, 8. 0, 8 is less than 1, like all the elements here in the sequence. But if you add 0, 3 to 0, 8, we obtain 1.1, which is of course greater than 1, and that's why it should not be in the sequence, and the sequence will end with 0, 8. So 1 here is an upper bound, is not necessarily an element of the sequence. While in linear space, the element you give, the second argument you give, is the end of the sequence. Must be the end of the sequence always. So you have two ways to define an arithmetic sequence, depending of the scenario you are in, depending on your algorithm, depending on what you want to generate, by giving a step or by giving a number of elements. The second way to generate a matrix is by defining a matrix with a given constant. For example, let's name it A, and we call function ones. Ones will generate a matrix with a given size. You have to give the size. For example, 2 rows, 3 columns, and all the elements of the matrix are equal 1. As you can see, 2 rows and 3 columns. Another function that also generates a matrix with a constant, a single constant, is zeros. So let's call it B, zeros, with S, zeros, and let's call it 2. I mean the number of rows. Give only one argument. If we give only one argument, we omit the second argument, then the second argument is equal to the first argument. So we have here 2 rows, and 2 columns. It's like you have entered 2. It's the same. So we have a matrix. All the elements are equal 0. And the third and last function that generates a matrix with a constant is I. So let's call it identity matrix. We generate the identity matrix I. And 3, we generate a matrix of 3 rows, 3 columns, and the identity matrix means that all the elements in the diagonal are equal to 1, and outside the diagonal are equal to 0. Now this is the identity matrix. It's a diagonal matrix. So this is for the second type of or second method to generate and initialize a matrix. The third method is to generate a matrix with random numbers. All the elements of the matrix are randomly chosen between a given interval. So let's give another example. Here A, and the function is called random, and you just give the size of the matrix. 2, for example, or let's say 3, or 5. So it will generate a matrix of 3 rows and 5 columns. And the elements generated are randomly between 0 and 1. 0 is not included, and 1 also is not included. Suppose, for example, I do not want to generate elements between 0 and 1, but between another interval. For example, between A equal -5 and B equal 3, for example. All the elements must be between -5 and 3, but randomly generated. So I write A equal A, small a, the left end point of the interval, plus random, the same size 3, 5, and multiplied by the length of the interval, that is B minus A. And because the element generated by random are between 0 and 1, but 0 and 1 not included, so here also the element generated will not include A and B. A and B will not be in the matrix, never. And let's type enter. And as you can see here, for example, -2, 95, -0.6, -4.4, all are negative here. Some are positive, 2.49, 0.05, and so on. They never exceed 3, and they never are below -5. They are in the interval area. But the matrix alone, random alone, will generate elements always between 0 and 1. Another function also that generates, let's call it B, that generate random values, but integers value. Integers means natural numbers, not real numbers. So a function is called rand I. We just add the letter I. And the first argument is the maximum of the integers. All the integers are randomly generated, but we need an upper bound. For example, 10. And 10 here is included. So the numbers will be between 1 and 10. 1 and 10 included, not 0. 1 and 10, between 1 and 10. And we give the size. For example, I don't know, for example, 3, 5. And we get a matrix, 3 rows and 5 columns. And all the elements are between 1 and 10. So we have 1 here, we have 8. We could have 10 here. 10 is included in the matrix. Let's generate it again. We get other numbers, of course, because random, each time you call it, it will give different values. So let's generate it again. And you can see here 10 is included, 1 also. Let's generate it again, and so on. So this is very useful because often you need to experiment with an algorithm. You want to test your algorithm, and you need an input, a matrix as an input. And so you have 3 methods to generate a matrix, either an arithmetic sequence, which always generate a row vector, a matrix with a single constant value, the identity matrix, and randomly chosen matrix with elements randomly chosen between inside a given interval, either real numbers or integers. So that's it for this second section. Let's move to the third section. So we clear, before any section, we clear all the variables we have used in this section, in this current section, and we clear the console to start fresh with a new section. Okay. So the third section is about how to access an element inside a matrix or a group of elements. So let's first define our matrix for this section. A equal 0, 1, 0, 3, and 0, 5. The first row, the second row, second row, 0, 2, 0, 4, and 0, 6. And we close any matrix just to show how to access an element in a matrix. So this is our matrix. Before to see how to access an element, let's see how to get the size of a matrix. We see here it is 2 rows and 3 columns, but we want that from Matlab. We call a function, and this function will return the size of any matrix, not only this one. So there is a function called size. So let's has two outputs, the number of rows n, m, and the number of columns, and as input the matrix A. And we type it. And as you can see here, m equal 2, the number of rows, and n equal 3, the number of columns. We can also call size with the second argument to get only the number of rows. If you want just the number of rows, type m equal size of a, the first dimension. First dimension means the number of rows. And we get, oh, I'm sorry, yeah. So when you do a mistake, you get, of course, a message, an error message. I meant a size. So we have m equal to. And when we do size a there, 2 means the second dimension. The second dimension is the number of columns. So we get n. We can also get the total number of elements. That is the number of rows by the number of columns, n by n. And the function is num element. Num element. The argument is a, and it will return the number of elements. L equals 6, which is n by n. So this is about the size of the function. The number of rows, the number of columns, and the total number of elements. A matrix is actually stored by columns. It's stored in an array, one-dimensional array, by columns. So the first column is stored 0, 1, 0, 2, and then the second column 0, 3, 0, 4, and then the third column 0, 5, 0, 6. It is stored by columns, not by rows. Not we store the first row and then the second. It is stored by. It is maybe due to history, because Fortran, when it started, Fortran is a very old language. When it started, the matrices in Fortran are stored by columns. So maybe and Matlab, the first version of Matlab, was written by Fortran, and bought by MathWorks. So it inherits maybe that feature. So anyway, whatever, the matrices in Matlab or Octave are stored by columns. So when we say, for example, A, the first element, we get 0, 1. And the second element is not 0, 3, it's 0, 2. Is 0, 2. And the third element is 0, 3. And so on. The last element is the sixth element, or you can just call it end. Function end will return the last index, which is equal here the number of elements. That is 6. End. Or you can also the number of elements which we have stored in L, here in L. The same. So here, when we want to access an element by its position in the array where we store the matrix. But generally, in matrix, we access the elements of the matrix by the number of rows, by its position in rows and columns. The index of the row and the index of the column. For example, we want 0, 4. 0, 4 is in the second row and in the second column. And we type A, 2, comma, 2. And we get 0, 4. We want, for example, the first row, the element in the first row, and in the third column. That is 0, 5. So we type A. The first argument is the number of the row, 1. And the second is the number of the column, or the index of the column, 3. And we get 0, 5. For example, I have made a mistake. For example, instead of writing A1, 3, I write 3, 1. So it's the third row and the first column. But there is no third row. It's only 2 rows. So we get here, of course, an error. And the error tells us that the bound is 2. 2 must the row index the row index must not exceed 2. That's how we can access an element, either by its position, by one single index, its position in the array, where the matrix is stored by column, or by the index of the row and the index of the column. We can also, for example, this element, we can also use AND, the AND of the row and the AND of the columns. So we can write here A, AND, AND. For example, 06. We can also use here, for example, the second column and the last element in the column in the second column. So we can write A, the last element in the second column. We can also use here AND to find the last index in the row or in the column. And we get 0, 4 as expected. We can also access actually not one single element, but what we call a submatrix, a small matrix inside the original matrix, the mother matrix. Or we can get the whole column, not one element in a column, the whole column or the whole row. How we do that? Let's define another matrix, but a little bit larger, to test this possibility, how to access a group of elements. So let's use random. We have seen random of integers. The elements should not exceed, for example, 20. And choose a matrix rather a little bit larger, 5, 7. 5 rows, 7 columns. And we type enter. So we have here a matrix, a large matrix, and we want to get only a part of it. For example, the matrix starting with the row 2, till the row 4, and from the column 2 till the 5th column, so 3, 4, and 5th. This matrix. These are not included. These are not included. So this matrix. This one. How we do that? Very simple. So what we do, let's call it small a equal b, parentheses. To access elements, use parentheses, not brackets. And you give the indices of the rows and the indices of the columns. And we said from 2 till 4 for the rows, and 2 to 5 for the columns. And we have seen this, actually it is a sequence. This is a sequence with the default step equals 1. So you write 2 colon 4, or you can write also a vector like this, 2, 3, and 4. But of course, and if the sequence is large, it's better, of course, to write 2 colon 4. But it's the same meaning, the sequence. It's not one number. It's a sequence of number with the step equal 1. With the step equals 1. And let's type enter and see. Yeah, as we said, 7, 5. 7. This is the second column from the row 2 till the row 4. And the 5th column, 10, 10, 20, 10, 18. This one. So this is how we can access a submatrix. This is called a submatrix. It is a matrix inside a matrix. We can also access submatrix, not necessarily all the columns are subsequent, or all the rows are subsequent, one after another. We can choose, for example, this column, and omit this one, and this column, and omit this one, and this column. So we have 2, 4, and 6. So we can write b, small b, equal b, and for the rows like previously, to 4, but for the columns, we enter them not a sequence, but as a vector. So the second column, not the third, but the fourth column, not the fifth, but the sixth column. And we got our matrix. So we have this one, 7, 5, 7, 13, 26, and 13, 150. So you have to give the set of indices for rows and for columns between parentheses. That's it. Very simple. So our window is now, console is full. Let's clear it, CLC, and continue. So our matrix B. Now I want to access the second column. That is this one. What we do like this, B, let's call it U. It is a column vector because it's a column. For the rows, it goes from 1 till the end. And the column is the second column. And I type, this is 6, 6, 7, 5, 7, 2. This is the second column. Or we can do better, we don't need to enter one end, we just enter the column. We meet the start and the end. And when the step is equal 1, the second argument here, the upper bound is always included in the sequence because the step is equal 1. So you can omit one end and just enter the column. All the elements in the second column will be stored in U. Same. And for the rows, let's say V, row vector, V, for example, the third row. We indicate the index of the row and all the elements in the row, column, and we type V. So we have the third, as you can see here, the third row of the matrix. So this is how we can access, how we can check the size of the matrix, the number of elements in the matrix, and how we can access the element of the matrix either by its position in the array where the matrix is stored as by columns, or a specific element by its row index and column index. And finally, as we have just seen, a submatrix, a column or a row. Column or row are a special submatrix with one single column or one single row.